Video for him. All right, let's get started. So we're going to pick up where we left off yesterday, which is finding the area under the curve of this function y equals f of x. And the way that we're finding the area under the curve is just approximating it with rectangles. Okay? So the problem that we looked at yesterday had a whole lot more rectangles than that this will do for us. If you're still working on that homework, which isn't due until tomorrow, the trick is to find the area of each rectangle and then add up all those areas. Okay, so it's maybe a little bit not as hard as it sounds, or maybe it's harder than it sounds. I don't know, but in this case, we are using rectangles all with the same width. Okay, we're going to call that width delta x. I think in that problem, I think it was like 0.25 or something like that. So, you know, if you have rectangle 1, rectangle 2, rectangle 3, and so on and so forth, the area of a rectangle is just the length times the width, or the base times the height. In this case, the base is that delta x every single time, or 0.25. That should be like just super basic. The hard part, if there's a hard part to be had on these problems, is to figure out the height. Okay? And in the first situation, if you're going with rectangles that are circumscribed, sort of outside, on the outside edge, if we're going to look at an overestimate, then you basically have a decision. Do you want to look at this side right here, or this side right here? Which one of those is going to go higher? Bless you. And so we're going to go up to this height right there, and you say, this is really where we kind of started losing focus. I felt like we're almost at the end of class. We're like, all right, how are we going to do this? How are we going to do this? How are we going to figure out how high it is? And somebody said, well, just go up to the function. Okay? This x value right here, in our case yesterday, was 0.25. So just plug in 0.25 into your function. Now this is where having a graphing calculator can become really helpful for you, because you can just plug in y equals 2 plus the square root of x, and then you can just use your little table feature of the calculator and have it ask you what's the x value. You plug in 0.25 and it'll tell you blah 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 blah, and that's going to be that blah 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 right there is going to be the height of this rectangle. So the area of the rectangle would be delta x times blah 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 blah. Then you move on to the next rectangle, and you ask yourself again the question, okay, which side do I need to go up here to figure out the height of the rectangle? Well, we have a function who happens to be continuously increasing, which is great, and we know that it's going to be this right-hand side over there. In fact, the right-hand rectangles are pretty much the best in every situation. So I've got a 0.25 is what this x value is. This x value right here was 0.5. So you just plug in 0.5 into your calculator and you get blee on the table. So the area of this triangle is going to, area of that rectangle is going to be delta x times blee. And then you just continue that same sort of process. You plug in, this one's going to happen to be in that situation we were looking at yesterday, the 0.75 value times the delta x. So bum, something like that. I don't know. Ho, ho, ho. Whatever happens to be the situation. So anyway, you'll take those areas, which is the width times the height, and you'll actually have numbers for them, and then you'll add them all up, and you'll get an approximation for the area of the total. Then you'll do the same thing again, but with an underestimate. So you say, okay, I want to go up this one and up this line, but I want to go to whoever's shorter, in which case it's going to be the one on the left. So you're going to plug in 0, and you'll get yes, or whatever. So you'll have a whole other set of areas. You take delta x times the yeses. And then you'll make a decision between these two, and you say, oh, it's at the 0.25. In which case you say, oh, that's great. I already have that value on my table. It was blah, blah, blah. And so you can plug in 0.25 times blah, blah, blah. And you can continue on for this rectangle. You want that one for this rectangle. You want this value. And you'll already have those y values provided for you in your table. And so then it's just a matter of adding them up, and the second time around it ends up being a lot faster. Did anybody have any question about kind of how to set that up? Okay, and once again, it's one of these things, if you haven't done it, you know, in a while, or if you haven't gone through that whole process, once you go through it once, then it becomes fairly straightforward. And if you need to, you can come by lunch B any day. I'm here 12:35 to 1:05. Also after school, pretty much every day. If you come right after school, I'm normally picking up my son, but I'm here like 5 minutes later. So by 3:45, I'm here. I normally don't leave before 4:30 or 4:45. So okay, so let's talk about this just for a minute, because this is where we're going to be starting from. I think we mentioned this yesterday. How could we make this process more accurate for finding the area under that curve and above the x-axis? Add more rectangles. And as I add more rectangles, though, what's going to happen to that width? It's going to get smaller. Okay, so we're going to have more and more rectangles. Now, if this was a pre-calculus class, I would say, all right, this one problem, go home and do it for 8 rectangles, then do it for 10 rectangles, then do it for 20 rectangles, and see if you come up with a pattern. Okay, see if it's getting closer and closer to a certain number. But this isn't pre-calculus, this is calculus. We have a way of sort of fast forwarding through that whole process to see what would happen if my number of rectangles would be 8, would be 16, would be 50, would be 800. What is that process that allows us to fast forward through that? The limit process. So we're going to set this thing up as a limit, okay? So we basically have, like I said yesterday, a few set of skills that we're going to develop. One is solve problems that are going to look like this. The limit as the number of rectangles approaches infinity of a sum of blah, blah, blah. Okay? We've got to figure out how to solve that. Then we're going to need to set up the area equals the limit of a sum. Okay? So we're going to learn how to solve this type of problem. Then we're going to learn how to set it up. Then step 3, we're going to set up and solve that. So that's the set up and solve. And basically the premise is that if you do figure out what is the limit as the number of rectangles approaches infinity, well, if you have an infinite number of rectangles that are infinitely small, and we see that it's approaching a certain number, then we can say conclusively that that is equal to the area under the curve. Exactly. Okay? This is no longer an approximation. It's an approximation when you have maybe 2 rectangles, or 10 rectangles, or even 200 rectangles. It's an approximation. When you have an infinite number of rectangles, and you are able to see that this process is getting closer and closer to a specific number, you can actually say with certainty, this is the area under the curve. Okay? So, let's do some of these limit of a sum problems. The first one we'll look at actually is in your book, number 40. The limit as n approaches infinity of the summation from I equals 1 to n of 2i over n times 2 over n. So we're going to apply our skills that we learned yesterday with summations first. And one of the things that I see here is that this n is not my counter variable. Counter variable is I. So what did I say we can do with something that is not a counter variable? Pull it out, because you can just technically factor that out. So we want to make that summation as simple as possible. So the limit as n approaches infinity, I'm going to put a bracket right here. We have an n in the denominator in both of those cases, so I'm just going to write that as 1 over n squared. Is there anything else I can pull out?
2.
Yeah, 2 2's. All right? 2 2's.
Why is it n squared not n?
2 n's.
Look, there's an n right there and there's an n right there. So, I mean, it could be, I don't know why they wrote it like this. They should have written it as just n squared. And then I could pull an n out. That don't make sense.
Luke is 4I over n squared.
Okay, right. Let me, intermediate step. Limit as n approaches infinity of the summation from I equals 1 to n of, let's simplify this first, 4I over n squared. This summation, they did not do a very good job. It's technically affecting all of that. So what they did is they wrote an unsimplified version here. Then we could simplify it. Then we say, oh, that 4 and that n squared, they don't affect anything. Summation from I equals 1 to n of I. I know why they wrote it like this. They wrote it like this because when we do that setup thing, when we figure out how to set it up, our setup is actually going to look something like this. So they kind of want you to see what it looks like before you actually set it up. Okay, does that make a little more sense, Kim? So, all right, hey, we know how to do this. We talked about that yesterday. Isn't that was it Goss? Good old Goss with his stuff there. So he's actually famous for some science stuff too. If you want to look into that. What was that formula?
N times n plus 1 over 2.
N times n plus 1 all over 2. Now we're going to get into a little bit of trickery here. So limit as n approaches infinity. This is 4n times n plus 1. So the numerator is going to be 4n squared plus 4n. The denominator is going to be 2n squared. All right. Now, do you remember when we have a variable approaching infinity of a ratio, there were some rules about when the numerator is bigger, you remember what happens to the ratio?
Increases.
Right.
Yeah, the whole thing, the ratio increases. So if the numerator has a higher exponent, then boom, numerator is going to win, it's going to approach infinity. What happens if the denominator is approaches infinity?
Approaches 0.
Yeah, then it's going to approach 0, okay? So what happens if they're a tie, like this situation?
Look at the coefficient.
We look at the coefficients, the leading coefficients. So you've got an n squared here, n squared here. So tie, well, it looks like the tie means we just look at the coefficients. 4 over 2, hey, that simplifies to 2. Congratulations, you've just added up an infinite number of things.
Cool.
Okay? If you look at this statement right here, just to give you an idea what we've just done, this says the limit as n approaches infinity of the summation from I equals 1 to n of 4I over n squared. What if n was equal to 3? Okay? We would have the summation from I equals 1 to 3 of 4I over 3 squared. That would be 4 times 1 over 9 plus 4 times 2 over 9 plus 4 times 3 over 9. You would end up with an actual number if n was equal to 3. If n was equal to 4, you would have the summation from I equals 1 to 4 of 4I over 16, which would be 4 times 1 over 16 plus 4 times 2 over 16 plus 4 times 3 over 16 plus 4 times 4 over 16. And you can come up with a number for that. Ladies, I need you to add this up. Gentlemen, any guys have a calculator? I've got 4 of them right over there. 1.6 for the 3? Great. 3/4 plus 1/2 plus 3/4.
2.5.
2 point what?
2.5.
2.5. And we could continue on this process, okay? We could say n equals 5, n equals 10, n equals 20, okay? As we go up and up and up and up, as we add things together, it's actually going to approach 2. Did I do that right? It's equal to 2.5? Okay. Alright, so let's do another one of these. That was number 40. Let's look at number 42. The limit is n approach to infinity of the summation from I equals 1 to n of 1 plus 2I over n squared times 2 over n. Okay. Well, at this point, we can ask ourselves, is there anything that's not affected by the I? And the 2 over n is not. So we can pull that one out. So we have the limit as n approaches infinity of 2 over n times, and then we have this term right here. Unfortunately, we can't just pull out like that 1, and we can't pull out the 2, we can't pull out the n, because it's all squared. Okay? So what we need to do is we need to expand that first. So this is going to be the first term squared plus 2 times the first and the second, so it's 2ab, so 2 times 2I over n, so it's 4I over n, plus the second term squared, so 4I squared over n squared. Then what we can do, now we can actually split this up, and if we're really good, in the process of splitting this up into 3 summations, we will also pull out what we don't need. So we have the limit as n approaches infinity of 2 over n times the summation from I equals 1 to n of 1 squared, well that's just 1, plus this term right here, everything that doesn't matter is the 4 over n, so 4 over n times the summation from I equals 1 to n of I, plus, in this term right here, the 4 and the n squared don't have anything to do with the I, so 4 over n squared times the summation from I equals 1 to n of I squared. Are y'all okay doing that, splitting it up and pulling the terms out at the same time? If not, then we could just write the summation of this, summation of this, summation of this, but just save a little time. We also pulled those terms out. Okay? So then we're going to apply our summation formulas so if we have a constant here, summation from I equals 1 to n of a constant is just a constant times n. So that's just 1 times n, which is this. Plus coefficient out here, 4 over n times summation from I equals 1 to n of I. And that's
n times n plus 1 over 2.
good old Gauss there, yeah. N times n plus 1 all over 2. Plus 4 over n squared. Now, I'm going to need a little bit of help on this formula. Rosemary's looking it up. okay, okay. N times, you said n plus 1, right?
2 and
2n plus 1 all over 6.
Awesome. Close parentheses, close bracket. Now at this point you're like, oh my gosh, am I gonna have to expand all that and FOIL all that and do all sorts of stuff? And the answer is, no, we're not. We're not gonna have to mess with that. We're gonna do some little tricks here. But we're gonna have to make it just a little bit more crazy. We're gonna take that 2 over n and we're just going to distribute that to each one of these terms, okay? So 2 over n times n is just gonna be 2. Plus, in the meantime, let's see what we can do here. That 4 and this 2, that cancels that 2 out, this turns into a 2. So out of 2 times 2, which is 4. So I have 4 n and n plus 1 all over, actually, that n will cancel out this n, right? Okay?
just 4 times n plus 2.
So 4 times n plus 1 plus.
What happened to the n underneath
Oh,
plus
you,
1?
yeah, you're right. Something that seemed right. Yeah, that n cancels out that n, but I still have that other n out there. I forgot about that one there. So yeah, so this is 4 over n plus 1 plus over n. Okay. Here, let's see, a 4 and a 6. So that'll reduce to a 2. This will reduce to a 3. I have that n can cancel out this n, but I still have an n squared down here. And I have a 2 right there. So 2 times the 2 gives me a 4. That n cancels out that n, so I don't have this one anymore. I still have the n plus 1. I still have the 2n plus 1. And in the denominator I have a 3 squared. Okay. So I'm going to do one more step where I don't want to FOIL everything. But this one right here, I can multiply it out real simply. That's just going to be 4n plus 4 over n. This term right here, I really don't feel like FOILing all this out. If you remember, I'm really just, I noted that I'm going to take the limit as n approaches infinity of this ratio. So all I'm really interested in is what is the highest power of n that I'm going to have here, and what is that coefficient? So if I have the 4 times the n times the 2n, that would be 8n squared plus blah, 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 all that other stuff if I were to FOIL that out. But I really don't care because I'm going to take the limit as n approaches infinity. So all that stuff doesn't really matter. So that's why I've got over 3n squared. You might remember that little trickery we did at the end, I think, of pre-cal. It's like, we're almost at the end of your pre-cal. How long does it take us? A whole semester. But anyway. So, as n approaches infinity, hey, 2, that's just going to stay right there. As n approaches infinity, we have n over n, those cancel. So we're just looking at the coefficient, so that's a 4. And then n squared over n squared, I'm just going to look at those coefficients. That's 8/3. So 8 plus 8/3.
6.
6 plus 8/3.
26 thirds.
26/3. Sure, there we go.
8.6666.
This one's saying 2/3. So, all right, congratulations. You have just added up an infinite number of things.
Yay.
Or more technically, you've looked and seen this is the pattern. If you were to add up more things and then more things and then more things, what is that approaching? Okay, great. Those are the skills which you need in order to solve the limit of a sum. You split it up, then you pull out the other factors, then you apply the formulas from yesterday, then you maybe just you distribute, do a little bit of simplification, and then apply your limit properties. Any questions so far? I have no doubt that you will do great on that part of the homework. So, let's move to the setup part. On page 269, number 50, it says, use the limit process to find the area of the region between the graph of the function and the x-axis over the given intervals, and then sketch the region. So, what we're going to do, and they have a problem, y equals x squared plus 1. So we're going to do a little bit of a x squared plus 1 is a parabola, which opens up. They want us to find the area under that parabola between 0 and 3. Okay, so we're gonna learn how to set up that limit of the sum process. Okay, let's start with the basics. What if I said just use one rectangle? Number of rectangles is 1. Okay. All right. Well, then maybe we would go here, have right rectangles here. Go to 3, and the area of that would be the width, which we'll just call that delta x, which is 3, times the height, f of 3. And you could solve that. Which, but what if I said, all right, I want you to use 2 rectangles. So, what would the width of that be? What would delta x be in that situation? 1.5. How did you arrive at that?
3 divided by.
Yeah, 3 divided by 2. So, my area would be 1.5 times f of 1.5 plus 1.5 times f of 3. So that one plus that one. What if I said there were 3 rectangles? What would my delta x be? 1. The length of my region divided by the number of my rectangles. So 1, 1, 1. So that would be 1, not 1.5, but just 1 times f of, going here to the end here, 1 plus 1 times f of 2, where that plus 1 times f of 3. Okay? So, question. What if I have n rectangles? What is my delta x going to be?
Total width divided by
3
n.
over n.
Total width, which is 3, divided by the number of rectangles, which is right there. And so, then the question is, what would my sum look like? Well, what would my area look like? My area would look like the width, so 3 over n times, I would go over just that amount right there, 3 over n and then I would go that high. So f of 3 over n plus the next rectangle, make sure I got the right one here, which would have a width of 3 over n.
Would be 3 over n times f, 3 over n times I.
And then times f of whatever this value happens to be, which would be 3 over n plus 3 over n, and plugging that into the function value. So I'd be going over 2 3 over n, so 2 3 over n's. Then for my next rectangle, the width would still be 3 over n, so I'm going to put 3 over n. And the height would be, well, I went this distance right here, which was 3 over n. Then I went over another one, which is 3 over n. Then I went over another one, which is 3 over n. So 3, so f of 3 times 3 over n. In fact, I could put a 1 right there. Are you beginning to see a pattern? Okay. So we could write this as the summation from I equals 1 to n of 3 over n times f of
3i over n.
I'm gonna put the I right here though, just to make it look like this. I times 3 over n. And that would be my summation statement for however many rectangles I needed. And then, if I said, okay, I want to figure out what is our pattern as the number of rectangles approaches infinity. So we stick a limit out front. So the actual area is equal to the limit as n approaches infinity of this. Now, what we didn't have earlier was a statement that looks like this. We're going to have to actually plug this into the function to get an answer. So we would say the limit as n approaches infinity of the summation from I equals 1 to n of 3 over n times, y'all said that was 3i over n. What is f of x in this case?
X squared plus 1.
X squared plus 1. So I'm going to plug in 3i over n into my function value. So that would be 9i squared over n squared plus 1. So 9i squared over n squared plus 1. Okay? And at this point, hey, that's just the limit of a sum like we've been solving all along. Alright, so let's see if we can do this super fast. I'm going to pull out that 3 over n since it has absolutely nothing to do with the summation. So the limit as n approaches infinity of 3 over n times, and I'm going to write the sum of this term plus the sum of this term. So in this case, that 9 over n squared has nothing to do with the counter, so I'm going to pull it out. So 9 over n squared times the summation from I equals 1 to n of I squared plus the summation from I equals 1 to n of 1. Then we'll apply our summation formulas that we learned. So the limit as n approaches infinity of 3 over, in fact, I might, if y'all are okay with it, I might do two things. I may distribute that 3 over n just to make things a little bit faster. That's going to be 27 over n cubed. Rosemary, are you ready? What was that formula again that you told us for the I squared?
Okay, I
Keep going, Rosemary.
Over 2
N times,
plus n.
but there's no
Times
Oh,
2n
good.
over
2n
plus
plus
1
1 over 6.
over 6. Okay. That seems a bit better. Plus, at the same time, I'm going to distribute that 3 over n to this. So 3 over n times, this is just summation from I equals 1 to n of 1, so that's 1 times n, so that's n. Limit as n approaches infinity. That 27 and the 6 reduce, that's a 2. That can reduce to 9. If we look at just the highest power that we're going to get, it's going to be 9, n, and the 2n. So 18n squared is the biggest power, or sorry, n cubed is the biggest power of n that we're going to get here. Technically it's going to be plus blah 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 blah, but I hate foiling. If I can avoid it, I will. Over 2n cubed plus those n's cancel and I just have 3. And then if we look here, numerator versus denominator, turns out to be a tie. You end up with 18 over 2, so 9 plus 3, the answer is 12. Area there is 12. And you may say, wow, there's a lot of these things are canceling out, and there's some nice answers, and some exact answers. There's got to be some sort of pattern here going on. The answer is yes, there is a pattern going on, and we will find that pattern and deal with it soon. Okay? But we do need to know how to solve this. So that's great for this particular problem. But what about like a more generic form? Okay? I mean, there was some special things going on here. Like for instance, we were from 0 to 3. What if we were from 0 to 5? Okay? Well, that's not too bad. There's that change right there. Okay? But what if we were going from like 1 to 5? What would be the difference there? So the more generic situation is you have any function, who cares what it's doing this. Okay, so starting from A and going to B, if I want to find the area under that curve and above the x-axis for y equals f of x, my entire width is this region right here, B minus A. That's the entire width. The width of one rectangle is going to be that entire region divided by the number of rectangles, exactly. So we normally say that's delta x, so that's equal to B minus A over n. Okay? And then your very first rectangle is going to, if we use right endpoint rectangles, use right endpoint rectangles, then our very first point right there is going to be A plus delta x. Our second point is going to be A plus 2 delta x. The third one is going to be A plus 3 delta x, and so on and so forth. And our function values, our heights, are going to be f of A plus delta x. a plus 2 delta x, a plus 3 delta x, and so on and so forth. Okay? So, what you would have for your area, if you're doing a right endpoint rectangles, is the limit as n approaches infinity of the summation from I equals 1 to n of delta x, that's the width, okay, times f of a, which are our lower bound, plus that, first one is delta x, then 2 delta x, then 3 delta x, so we would say delta x times I. Now, in our situation that we did just now, you say, well, we didn't have anything that a plus or whatever. Yeah, we did. It's just it was 0 in that case, so we didn't have a 0 plus in any of those. But if we were between like 1 and 5, then we would have 1 plus delta x, so on and so forth. Sometimes in some calculus books, they'll write it like this: the limit as n approaches infinity of the summation from I equals 1 to n of delta x sub I times f of a plus delta x. They'll put the I right down there, which I think is really misleading. So don't even bother writing that down. This is the better formula. And obviously remembering that delta x is b minus a over n. So it really helps if you sort of figure out what b minus a over n is. Then you can evaluate that inside the function. Then you got the whole thing set up and you can plug it in. Okay? Now you say, all right, Mr. Goddard, that's for using right endpoint rectangles. Is there another formula for left endpoint rectangles? Or from circumscribed or inscribed and stuff like that? Well, for left endpoint rectangles, there are, but you've got to change that delta x. You don't have the a plus, but you've got to handle the very last situation. If we use right endpoint rectangles, the formula is actually very simple. And what's even better is, in the end, it really doesn't matter. It doesn't matter if you're using right endpoint rectangles to approximate the area, okay, or whether you're not using left endpoint rectangles, okay, because in the end, all of those rectangles are getting infinitely small, and we're adding up an infinite number of them. So whether you're approaching it from an overestimate and getting closer to the correct answer, or an underestimate and getting closer to the correct answer, you're still going to get to the correct answer no matter what. Okay? And last year in pre-calculus, sometimes we did circumscribed rectangles and sometimes we did inscribed rectangles. The problem that we discovered, maybe you can remember, is that whether you have circumscribed or inscribed rectangles depends on whether or not your function is increasing or decreasing. If you remember, I don't know if you remember that. But circumscribed, sometimes it's left endpoint, sometimes it's right endpoint. And it's really impossible to generate a generic formula that's going to work every single time, because we don't know if the function is going to be increasing or decreasing in what region. If we just say right endpoint rectangles, boom, every single time we know it's going to be this point, then it's going to be this point, then it's going to be this point, then it's going to be this point. We can put it into that limit of the sum. This is probably the most calculation intensive process that we will do this entire course. Okay? If you can get it through, if you can get through the limit of a sum, and I can say everything else is going to be smooth sailing, but it will be smoother sailing. Alright? Your homework. 39, 41, 43, 47, 49, 51. Just 6 problems, 2 on Thursday. Tomorrow, yesterday's assignment we did.
It's okay, I have messages from my dad, doesn't accident.